Happy New Year! This is Miss Nakayama, and I'm really sorry I'm not with y'all again, but I will be back soon. So y'all do what you're supposed to do, and everything will be great. Today's lesson is 6.1a, Exponential Growth and Decay. And if you did your warm-up and you used the link in Desmos, then you have some idea of the functions that we are talking about. In the warm-up, it looked like y equals a times b to the x, okay? The parent function is just y equals b to the x. B is always greater than 1. Can't be, it can be between 0 and 1, as you saw in your warm-up, okay? And, but it will never be negative. It just doesn't make sense for it to ever be negative. It's not possible. So what do you need to know about this graph? It is continuous. It is 1 to 1. And it is always increasing. The domain is all real numbers, also written in interval form would be negative infinity to positive infinity. The range is all positive real numbers. That's 0 to infinity and does not, I didn't want to put those key points in there yet, does not include 0. Your asymptote is the x-axis, which is the equation y equals 0, and you have an intercept of 0, 1. Those are key features that are on every parent function, y equals b to the x. Now, as you know, I'm always about key points so that we know how to easily graph these functions. And our key points are going to be negative 1, 0, and 1. And if you put 1 into this function here, if x is 1, then of course y is b. And that gives us that point on the graph, 1 comma b. If x is 0, then y is always 1, which is our y-intercept of 0, 1. And if it's negative 1, it's b to the negative 1, which is 1 over b. And that's an easier way to think about it. Negative 1, 0, 1, b, 1, and 1 over b. These two are always reciprocals of each other. Okay? So let's talk about graphing them. Tell whether each function represents an exponential growth or exponential decay, then graph the function. So you had a little bit of that in your warm-up, but the key is always going to be whatever that b, too many b's there. All right, b is greater than 1 is going to be growth. B is less than 1 is going to be decay. So you got to be able to identify the b, which is the base of your exponential function. So in this first one, b is greater than 1, so I know that I have growth. And my key points, we just talked about, I'm going to have negative 1, 0, and 1. And then I'm going to start with my b down here at the bottom, and it's going to be 2, always 1, and the reciprocal of 2, which is 1/2. And my y-intercept is, my asymptote is y equals 0. So my graph, I went ahead and put those on there. It looks like this. Okay, here's my dotted line right here. That's my asymptote. Asymptote is always dotted. And you can see the key points right here, negative 1, 1/2, 0, 1, and then 1, 2. Now, if b is 2, y'all, then every y value is multiplied by 2. That's the difference in an exponential function versus a linear function. We are multiplying by the same thing every time instead of adding the same thing. So if I know this is 1, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. It's going to give me the next point. Okay? All right. So let's look at y equals 1/2 to the x. My b in this case is 1/2. That is less than 1. So this is going to be decay. My key points, again, negative 1, 0, 1. And then I'm going to have 1/2, 1, and the reciprocal of 1/2, which is 2. Asymptote is still y equals 0. And my graph looks like this. So I picked, again, this is negative 1. Well, this is negative 1, 2, 0, 1, and 1, 1/2. Those are the key points. But sometimes if I want to fill up my graph, then I know, okay, times 2 gives me 4, times 2 gives me 8. So I'm just filling in the points. Looks like that point should be up 1. I misgraphed it. But it's the same concept. That's what's happening each time to our graphs. Okay, so transformations, y'all. Same old you've been doing. Okay, where does it show up in our exponential functions? Okay, we're going to have A, just like you saw in the warm-up. H, okay? H is always with X. K is always with Y, all there by itself. H describes the horizontal translation. If it's positive, it moves to the right. Negative, it moves to the left. K describes our vertical translation. If it's positive, it moves up. If it's negative, it moves down. Remember that when we talk about the change or what it looks like, it's always the opposite with H and the same with K. All right, and A is basically describing our orientation and shape. Okay, orientation, because if it's negative, it goes, it's reflected in the x-axis. I don't want to say it goes down, but it's reflected in the x-axis. That's the change. And then if the absolute value of A, so disregarding the positive or negative of it, if A is larger than 1, it's stretched vertically. If A is between 0 and 1, it is compressed vertically. So it's going to be shrunk. And again, you should have seen that in your warm-up. But keep in mind, remember we talked about the negative, it's not ever, A is always between 0 and 1 or greater than 1, because if it's negative, then it's reflected. And that's not talking about the shape. So let's do a few of these graphs. All right, when you look at y equals 2 to the x plus 3 minus 5, the first thing and the most important thing to be able to do is to identify your b. What's the base of this function? The parent function. And that's y equals 2 to the x. So my base is 2. Okay? And that means when I get into my key points over here, I'm going to have negative 1, 0, 1, and then I'm going to have 2, 1, and 1/2. And my asymptote is y equals 0. Now, we got to talk about all the changes. Anything that is extra that's been added from my parent function of y equals 2 to the x. So this is just y equals 2 to the x. What's over here that's not y equals 2 to the x? I got a 3, which is h, and it does the opposite of what it looks like, so it moves to the left. 5 is the same, so it's going to move down. So all you have to do is take those key points, all right, every key point, and I'm going to, every x value is moving to the left, so I'm subtracting 3 from every x. Y value is moved down, so I'm going to subtract 5 from every y value of my first key points right here. So negative 1 minus 3 is minus 4. 0 minus 3, and 1 minus 3. And then I'm going to have 1/2 minus 5, 1 minus 5, and 2 minus 5. And I'm pretty sure, okay, this asymptote of y equals 0, okay, what did I do to every y coordinate? I subtracted 5. So I'm going to subtract 5 from my asymptote and find out that that's y equals negative 5. So it is a good practice to do all 3 of these points. I believe in Delta Math, you only have to graph 2 of them. But then you're always safe because you only have to graph the ones that are not the fractions. But you won't know which ones are going to be it until you've done a lot of them. Okay, so what does my graph look like? I went ahead and graphed it for you. Again, asymptote is dotted, okay, and you can see how each of the points corresponds. Last thing we have to do, state the domain and range. All right, my domain is always all real numbers. And my range, if you notice, my graph got shifted down 5 units. So that means that now instead of going from 0 to infinity, it goes from negative 5 to infinity. And that's our domain and range. All right, look at this next example. Y equals negative 3 times 2/5. Notice anytime you have a fraction, y'all, with our exponential function, you have to put parentheses around them. So if you don't do that in Delta Math, it will be marked wrong. Negative 3 times the quantity of 2/5 to the x minus 4 plus 2. So again, what is your b? Your b in this case is 2/5. So my key points still have negative 1, 0, and 1. But B at the bottom is going to be 2/5. And then I'm going to flip, 0 is going to give me 1, and I'm going to flip it to 5/2. So again, this is my parent function of y equals 2/5 to the x. So when you have to describe things or you're looking at the changes that happen on this function, you're looking at anything that's in here that's not right there. So you have, yes, a -3, but if you ever had to describe it, you have to talk about two different things, because the negative, flips it over the x-axis. The 3 is that a value that's bigger than 1, so it's going to be a vertical stretch. The 4 is up there with the x, so that means it's a horizontal shift of right 4 units. And the 2 is outside here, same, and so that one's going to go up. So, and actually one thing I forgot to mention, the original asymptote, y equals 0, you always want to write that. And so let's go change each of our points and find out what happens. So for each x value, I'm just going to move to the right. So that means I'm adding 4 to each of those. Probably should just put a +4. Add 4 to each of them. Now, if you notice on the y coordinate, I have up and I have a vertical stretch. So I'm doing two things to it. Technically, if you want to think about 3, but I multiplied by -3 and I added 2. And it will matter, y'all, if you do not follow the order of operations. So order of operations says we do multiplication and division before addition and subtraction. So I'm going to multiply everything by -3, and then I'm going to add 2. So looking at my x's, -1 plus 4, 0 plus 4, and 1 plus 4. 5/2 times -3 plus 2. Get your calculator out if you need to. -11/2. 1 times -3 plus 2, of course, is -1. And 2/5 times -3 plus 2 is 4/5. So in this case, we weren't able to avoid a fraction. Plot whichever one's easiest to you. The y coordinate, y equals 0, multiply by -3, add 2, that's going to become y equal 2. So my graph is going to look like this. Okay, -11/2 is down here. Okay, that's 3 at -5.5. And then at 5, it's just underneath 1. But at 4, -1, we have that point. Okay, again, got to give my domain and range. Domain is all real numbers. Range, all right, remember. This one got flipped over. So the lowest point on your graph is down here, and the highest point is up here. And whenever you give interval notation, you have to give the lowest number, smaller number first. So this is going to be from -infinity all the way up to 2. Again, not inclusive because that's your asymptote. And that is your domain and range. All right, last thing, this won't take long to talk about, is the model functions that we use for exponential growth and decay and word problems, okay? And they look like a of t is equal to a times 1 plus r to the t, or a of t equals a times 1 minus r to the t, okay? Y'all, this is very similar to what you've just been dealing with. We were dealing with y equals a times b to the x, okay? So what's different is that this whole thing in the parentheses is your b. But obviously, if you have growth, then you're adding the rate. And if you have decay, then you are subtracting the rate. That's the only difference in these two things, between this and this right here. And the rate is given to you in the problem, okay? The other thing to pay attention to is t describes time, but in these problems, time can be any unit. It can be hours, minutes, seconds, years, days, weeks, any unit of time that's acceptable. When we ever talk about money problem, time is always in terms of years, but that's not the case with these. All right, so look at these last problems. Example 3, we have 2 or 3 word problems, real short. A virus spreads through a network of computers such that each minute, 25% more computers are infected. If the virus began in only one computer, graph the function for the first hour. Actually, I don't want you to graph the function. I just want you to write a model for the spread of the virus, okay? Spreading through the network, 25% more computers. So you got to decide, is this growth or decay? And I hope you all realize quickly it is growth. Don't know why all that's happening. Hope you aren't seeing it. Anyway, it's growth. So if it's growth, then my model is up there on the left, and I'm going to have 1 plus A of t is 1 plus something, or A times 1 plus something. So 1 is what it starts with. It's a virus, okay? A virus spreads through a network of computers such that each minute 25% more computers. So I have 1 representing the original amount, and then it's 25%. That's my growth rate, and that's what it changes. And we simplify that to 1 plus 0.25, which is 1.25. You don't have to have the parentheses around it anymore. All right, look at this one, example 4. This is the last example. We should do these two. A cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of caffeine from their system per hour. So, somewhere, I forgot to give you, you're supposed to write a model for that problem. Okay, so is it growth or is it decay? A cup of green tea contains so much caffeine. The teen is eliminating the caffeine every hour. So this is an example of decay. So that means that I'm going to have 1 minus something. I've got to figure out what A is my original amount. My original amount is 35 milligrams. My R is the rate that it's leaving the system. So R is 12.5%, but I have to write that as a decimal, which is 0.125. And 1 minus 0.125 is 0.875. So my simplified version would be A of t equals 35 times 0.875 raised to the t. You can use the parentheses, or like up here, you can use the dot, whichever one you want to. Now, last thing, estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of tea. Okay, so after 3 hours, that means that t is, of course, representing my time. So I'm going to go calculate A of 3. And A of 3 means go put 3 in for T. So I put my 3 in, put it in my calculator, and find out that you still have about 23.4 milligrams of caffeine in your body 3 hours after drinking that green tea. So that is all I have for exponential growth and decay. I believe y'all seen it before, so it should be a relatively easy lesson. Do your best. Email me, let me know if you have any questions. Thank you so much for watching, and y'all have a great day.